You are drifting through a region of space where the stars have begun to warp and smear into a ring of fire. The momentum carrying you toward that central shadow is already irreversible. A stellar mass black hole would have already ended this journey. If this were a smaller object, the gravitational gradient would be steep enough to pull you apart while you were still millions of miles away. But this is a supermassive black hole. Because its mass is billions of times that of our Sun, its physical size is enormous, meaning the gravitational pull is distributed over a vast area. The tidal forces here are actually quite gentle, allowing you to survive the approach without even realizing you've passed the outer limits. Your first major threshold is the photon sphere. For a static black hole, this boundary exists at exactly 1.5 times the Schwarzschild radius. Gravity is so intense at this distance that photons are forced into circular orbits. Instead of radiating away into the void, light is captured and dragged around the circumference of the black hole. If you look straight ahead while standing at this radius, you will see the back of your own head. Light reflecting off your body has traveled the full circuit of the sphere and returned directly to your eyes. Even before you reach the final boundary, the black hole has overridden the basic mechanics of sight. Your perception of reality is already beginning to fracture. To understand the nature of the fall, we have to look at it through the eyes of an observer watching from a safe, distant orbit. As you descend, the outside observer sees your clock slowing down. Your image reddens and dims due to extreme gravitational redshift, appearing to freeze just above the horizon. To them, you never actually cross over. You simply linger at the edge, eventually fading to black. From your perspective, however, time proceeds at its normal pace. You cross the event horizon in a finite interval, noticing no physical barrier or change in the local environment. This is where the light cones tilt inward toward the center. Within the event horizon, the radial direction toward the singularity has mathematically replaced the role of time. Because the downward direction is now a temporal one, the singularity is a moment in time rather than a location in space. You hit the center not because you traveled a distance, but because you reached a point in your future, making the collision as chronologically certain as the arrival of the next second. Looking back at the universe you left behind reveals a narrowing halo of light. Relativistic aberration and beaming concentrate the view of the entire outside world into a single blinding dot directly above you. The light entering the hole from the outside world piles up behind you, blue shifting into high-energy X-rays and gamma rays that would eventually roast any material object. While the approach was gentle, the descent into the interior is characterized by a violent physical transition. This is spaghettification. The gravitational pull on your feet is now vastly stronger than the pull on your head, which stretches you vertically and compresses you horizontally into a stream of subatomic plasma. If the black hole is rotating, the dynamics can shift toward pancakeification. In this scenario, the forces reverse, squashing you flat from head to toe while expanding your remains laterally. Whether you are stretched or squashed, your physical body is destroyed well before you reach the center. Only raw quantum information survives to continue the fall. In a rotating black hole, that information encounters one final boundary, the inner horizon. Here, you hit the mass inflation instability, a wall of diverging radiation where light from the outside universe piles up and becomes infinitely blue-shifted. General relativity fails to describe the physics of this region. To understand what happens past this wall of energy, we would need a complete theory of quantum gravity. Without it, the absolute center remains a mathematical breakdown. The existing math suggests bizarre possibilities. In a spinning Kerr black hole, you might enter a wormhole or emerge through a white hole into a mirrored region of space known as the antiverse. There is even the possibility of closed time-like curves, where the geometry of space allows you to loop back into your own past, repeating the same sequence of events indefinitely. The center of a black hole represents the coordinate end of our current physics, where the curvature of space-time becomes infinite, and all causal links to our world are severed. If the only way to see what lies beyond this breakdown is to leave our universe behind forever, would you still take the fall?